Next chapter is astigmatic lenses. So we have done with spherical lens. In a spherical lens, all the meridians, whether this meridian have the same curvature, so refraction is symmetrical, and there is formation of a point image of a point object. Point object means focus. Point object and point image or a focus point. Now in astigmatic lens, the difference is that the meridians do not have the same curvature. So this meridian and this meridian, so both meridians are different, have different curvature. This one is steep and the other is flat. One is steep and the other is flat, and the formation of a line image, a point object. So there is no formation of point image, there is formation of a line image. There are two types of these astigmatic lenses. One is cylindrical lens and another is toric lenses. So first of all, cylindrical lenses. In cylindrical lenses have one plane surface. So one is plane surface, as you can see in this image, one surface plane, and the other forms part of a cylinder. The other forms part of a cylinder. Thus, in one meridian the lens have no divergence power, and this is called the axis of cylinder. In the meridian at right angle to the axis, the cylinder acts as a spherical lens. So this is a spherical lens. The total effect is the formation of a line image of a point object. As you can see, this is a line image. This is called the focal line. It is parallel to the axis of the cylinder. This is parallel to the axis. This is axis. As you can see, this is axis. So the focal line is parallel to the axis. Now maddox rod. This is maddox rod. It is a useful device. It is used in the diagnosis of extraocular muscles imbalance. It consists of a series of powerful convex cylindrical lenses. Powerful convex cylindrical lenses. These lenses are mounted side by side in a trial lens. Suppose this is one cylindrical lens. So like these lenses, a number of lenses are mounted side by side. The patient views a distant white point source of light through the maddox rod, which is placed before the eye in the trial frame. So the patient will see a white point source of light, and that spotlight must be far enough away for its rays to be parallel on reaching the patient. So they must be at least 6 meters away. So as we know that light incident on the maddox rod in two planes, in the meridian parallel to the axis and on the meridian at 90 degree to the axis. So parallel to the axis they pass undeviated, and in 90 degree to the axis it is converged and form a line. So the light which pass undeviated, so it is brought to a focus by the eye, by the cornea and by the lens. Since maddox rod consists of a row of cylinders like this one, so a row of points of foci are formed on the retina and seen as a line of light. So the retina sees it is a line of light, and this line will be at 90 degree to the axis of the maddox rod. So the glass of the maddox rod is tinted red, so the composite line image seen by the patient is also red, and meanwhile with the light which is incident in the meridian 90 degree to the axis, it is converged by each cylinder to a real focal line which is between the rod and the eye. This focal line is too close to the eye for a distant image to be formed on the retina by the focusing mechanism of the eye. So this light is therefore scattered over a wide area of retina and does not confuse the perception of the composite line image which is described above in the above picture. So remember that the red line seen by the patient lies at 90 degree to the axis of the maddox rod and is formed by the focusing mechanism of the eye. It is not the real line image of the maddox rod. Now use of the maddox rod to test muscle balance. Now to test maddox rod, to test muscle balance, this is the maddox rod. It is placed in the trial frame in front of one eye. So in this context, it is in front of the right eye, as you can see. So the patient view the distant white spot light with both eyes. Now to test for horizontal balance, for horizontal deviations, the rod must be horizontal and the patient will see a vertical line. The patient will see a vertical line is shown in these pictures. So, and to test the vertical imbalance, the rod must be vertical and the patient will see a horizontal line is shown in these pictures. So the right eye therefore sees a red line. This red line is 90 degree to the axis of the maddox rod. So the axis is horizontal, the line is vertical. While left eye sees the white spotlight. So the right eye line and the left eye the white light. So thus the two eyes see dissimilar images. So both eyes are dissociated and allowing any muscle imbalance to become manifest. So remember, while interpreting the results, that the eye behind the maddox rod, in this case the right, so the eye behind the maddox rod is deviated in the opposite direction to that indicated by red line. So the red line and the eye are opposite to each other. So there are three results. If both the line and the white spot are coinciding, so there will be horizontal orthoporia. If the red line is on the right side, so this is uncrossed image, so this is isoporia. And if the red line is on the left side, this is cross image, so there will be exoporia because the eye deviates on the opposite side of this line. So this is exoporia. And same as for the vertical, if both coincide, this is vertical orthoporia. If red light is above, this is hypoporia because the eye deviates on the opposite side. Red line below, so this is hyperporia. Any deviation is measured by placing prisms. So we can measure this deviation by placing prisms before the left eye until orthoporic situation like this is achieved. Toric, now we will discuss toric surface. So toric surface, now imagine that the cylindrical lens is picked up by its ends and bent. So this was suppose the cylindrical lens, but it is bent. So the XY which was previously straight, it has now become an arc of a circle. So now both are bent. In the cylindrical one was straight. So the previous cylindrical surface is now curved in both its vertical and horizontal meridian. Previously only one meridian was bent in cylindrical lens, and in toric both are bent, but not to the same extent. Both are bent but not to the same extent. Now this is called toric surface. The meridians of the maximum and minimum curvature, they are called principal meridians, and in ophthalmic lenses these are at 90 degrees to each other. Now the principal meridian of minimum curvature and therefore minimum power is called the base curve. Toric lenses are spirocylinder lenses. Toric lenses are the lenses with one toric surface. They are also known as spirocylinder lenses. Toric lenses do not produce a single defined image because the principal meridians form separate line foci. As you can see, first focal line and second focal line. The one meridian forms one focal line and the other meridian form another focal line separated by a distance, and they are at right angle to each other. Between these two line foci, as you see, the rays of light form a figure known as strum conite. This is known as strum conite after the mathematician Strum, who described it in 1838. The distance between these two line foci is called the interval of Strum. The interval of Strum. The plane where the two pencils of light intersect is called the circle of least confusion. So here both the lines intersect, and this is called circle of least confusion. So this is one meridian form one focal line, and the other meridian form this focal line. The first focal line is vertical to this, formed by this horizontal meridian, and the second focal line is horizontal and it is formed by the vertical meridian. Blurred circles, the other circles on both sides of the circle of least confusion are blurred, and they lie between both these focal lines. So a toric lens can be thought of as spherical lens with a cylindrical lens superimposed upon it. So why it is called spherocylindrical lens? Because a toric lens can be thought of as spherical lens with cylindrical lens superimposed upon it. Spherocylindrical lens. For example, a toric lens with a power of +2 diopter in one principal meridian and +4 in the other. Suppose one is +2 as shown here and the other is +4. This is +4 and another is +2. So +4, this is +4 and this is +2. So this can be regarded as +2 diopter sphere. So this is +2 sphere, and in this meridian there is +2 cylinder superimposed on the spherical lens. Now spherical equivalent. Now it is sometimes useful to calculate the power of a spherical lens closest overall effect to a given toric lens, known as the spherical equivalent. So this is the spherical lens, power of spherical lens, which is close to the power of the given toric lens. This reveals whether the eye is essentially hypermetropic, emmetropic, or myopic. This consideration is especially important in the choice of intraocular lens power for the individual patient. The spherical equivalent power is calculated from the toric lens prescription by algebraic addition of the spherical power and half of the cylindrical power. Spherical plus half cylinder. Suppose the spherical is plus 2 and cylinder is also plus 2. So the equivalent will be plus 3. While that of plus 2 minus 2, the equivalent will be plus 1. Plus 2 and algebraic addition of minus 1, so it gives plus 1. The focal point of a spherical equivalent would coincide with the circle of least confusion of the toric lens strombolites. The last topic is cross cylinder. This is cross cylinder. This is a type of toric lens. It is used during refraction and it is used to check the orientation of the trial cylinder, to check the axis, and to check the power. So it is used to check the axis of a trial cylinder, and it is also used to check the power. To check the axis of trial cylinder, this is placed obliquely. The axis of this lies obliquely to the axis of trial cylinder. So to check the axis of this lies obliquely, and to check the power, it is placed in the same axis as the trial lens axis. To check the power, the axis of both are lying samely. The axis of trial and cross cylinder lie same, while to check the axis of this Jackson cross lies obliquely to the axis of trial lens. So this is a spherocylindrical lens. In this Jackson cross, the power of the cylinder is twice the power of the sphere, and they both have opposite sign. Net result is thus the same as superimposing two cylindrical lenses. It is like these are two cylindrical lenses of equal power, plus 0.5 minus 0.5, but opposite sign, and their axes are at right angle. As you can see, the axes are at right angle. The lens is mounted on a handle. This is the handle. It is placed 45 degree to the axis of cylinder. 45 degree. The axis marked on the lens. So these axes which are marked, they have actually no power of the individual cylinder. Actually the power of this cylinder lie at 90 degree to the marked axis and coincide with the marked axis of no power of the other cylinder. So the axis of minus 0.5, the power of this minus 0.5 coincide with plus 0.5, and the power of plus 0.5 coincide at 90 degree, actually at the minus 0.5. Cross cylinder are named by the power of the cylinder, and this is marked on the handle. The cross cylinder would be designated as one diopter cross cylinder because they are named after the power of the cylinder. cross cylinder are available in two powers, 0.5 and 1 diopter. The 1 diopter cross cylinder is used to check the axis of trial cylinder and the power in patients with poor visual acuity. So +1 for poor visual acuity and 0.5 for good vision. Power in the patient who have good vision. Clinically, the cross cylinder is used to check the axis and the power. So if you want to check the axis, so again the power of this is actually this, because they lies opposite. Actually here the power is +0.5 and here minus. And the power the cross cylinder, this is actually 1 diopter cross cylinder, because the cross cylinder are named by the power of the cylinder. Now how to use this? Now the cross cylinder is used to check the axis of the cylinder prescribed, and then after checking the axis, then we check the power. First the axis and then the power. It can also be used to verify that no cylinder correction is necessary for the patient if no cylinder was detected on retinoscopy. First, the patient is asked to look at the line of test type, 2 lines above the smallest he can see. Why 2 lines above he can see? Because this cross cylinder blurs the vision, and larger letters are used to make discrimination between the positions of cross cylinder easier for the patient. Now how we check axis? First, the cross cylinder is held before the eye, the handle in line. This is the handle. To check axis, the handle should be in line with the axis of the trial cylinder. So it should be in line with the axis of trial cylinder. The cross cylinder is then turned over. This is then turned over. The patient is asked which position gives a better visual acuity. The cross cylinder is held in the preferred position in which the patient has better visual result. So the cross cylinder is held in that position, and the axis of the trial cylinder rotated slightly towards the axis of the same sign on the cross cylinder. So this process is then repeated until the trial cylinder in the correct axis for the eye. So at which time rotation of the cross cylinder will offer equally unacceptable visual alteration to the patient. Now how to check power? To check the power of the trial cylinder, this cross cylinder is held with first one axis and then the other overlying the trial cylinder. So actually first this axis and then the other axis. To check the power of trial cylinder, so the cross cylinder is held with first one axis like this +0.5 and then the other overlying the trial cylinder. This has the effect of increasing. It is like if we increase and then decrease the power of the trial cylinder. To confirm the absence of cylinder, the cross cylinder is offered as in addition to the trial sphere in 4 different orientations. So we can also use it in addition to trial sphere with axis first at 90 degree, then 180, then 45 and then 135. If the patient prefer one of these options to the sphere alone, then a cylindrical correction is necessary. The exact axis and power can then be determined by the methods described above. To achieve the best result from the test, it is important that the patient has the clearest vision possible before the cross cylinder is used.